Hello, in this video we are going to cover two more reactions in the alkyne unit, and those two reactions are going to be reaction 9E and 9F. Before we do that, I do want to talk about a type of isomerization called tautomerization between a keto group and an enol group, or keto molecule and an enol molecule. For most of you, I know this is new terminology. Don't worry, we'll go over what these two terms mean. But what's not new are the names of the two reactions we're going to go over in this video: acid-catalyzed hydration and hydroboration oxidation. Hopefully you remember these two reactions from your alkene unit to make alcohols. So there's going to be some similarities between hydration of an alkene and what we're going to go over right now, hydration of alkynes. Do you remember the differences between the acid-catalyzed hydration and hydroboration oxidation? One, you add water in a Markovnikov fashion, and in hydroboration oxidation, you're going to add it in a non-Markovnikov fashion. Hopefully you're familiar or you're comfortable with these in the context of alkenes. You'd want to review that first before trying the hydration of alkynes. But let's talk about Keto-Enol Tautomerization first, because that's going to be relevant to our hydrations. Keto-enol it's a type of isomerization, but it has a special name, tautomerization. It's not resonance. Okay, resonance, atoms move. We're literally making isomers when this process happens, and it's when when two molecules, two constitutional isomers, I should say, interconvert in solution. Okay. And the simplest example of a keto-enol tautomerization is this. Let's say we have acetone, and again, it's not resonance, it's an equilibrium. It's going back and forth, and its isomer partner would be this molecule here. Okay. You know that this is a ketone, and this is actually an alcohol alkene. But they shorten the names, and we're going to call this the keto form, and this is the enol form. You see where they got the name enol for alkene, alcohol, enol. Okay. And this happens in solution. And what you want to be good at is converting back and forth. So before we look at possible mechanism, if I have this kind of enol, so let's start with the enol. How do we recognize an enol? We recognize an enol because there's a carbon-carbon double bond, and off of one of those carbons is an OH group. Okay. How do we go back and forth between an enol and the keto? Or how do we draw the two? All you have to do is bring the double bond over to the oxygen and get rid of the hydrogen. I said these are isomers. Are they really constitutional isomers? They have to have the same molecular formula, but different connectivities. This is C6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. H10, O. This one, C6 again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. O. You could think of it as this hydrogen going onto this carbon. See, this carbon has one hydrogen. Now this carbon has two hydrogens. Okay. Now, where can things get a little bit complicated is this. If you had an asymmetrical ketone, okay, this is called the keto form again, then how do we go now to the enol? Well, we're going to shift the double bond to one of the sides. And actually this has two enol forms. You could have an enol like this, and you can have an enol like this. Right? Both of those are enols. And this is a keto. And really we should be saying keto form and enol form. Okay. Does this happen in solution? Yes. Now it goes faster, the bouncing back and forth goes faster under acidic or basic conditions. I'm not going to show you both. I'll show you the acidic version. And I'm going to start out with an enol. In the reactions that we're going to see today, the hydration reactions, either Markovnikov or non-Markovnikov, the initial molecule you make is actually an enol, but it isomerizes or tautomerizes into the keto. So what I should have also mentioned before moving on is the keto is typically more stable. Usually. So that usually the keto is more stable than the enol. Okay. That's because a carbon-oxygen double bond is stronger than a CC double bond. So there's the thermodynamic motivation for the molecule to mainly look like this. In terms of percentages, I don't know. It could be 95% to 5%, something like that. But again, keto is the more stable. Keto is the more stable. Keto is the more stable. Okay? Because in our reactions, we're going to initially make an enol, and due to the stability of the keto form, you're going to change it into the keto group, or the keto form. So, I was going to do the mechanism. And I'm going to do it under acidic conditions. So the mech under acidic conditions. Okay. Let's see, what are we going to do first? Let's have an acid, so it's acidic. We're going to protonate something. We have a double bond here. Now, yes, it is tempting to protonate the oxygen, but nothing happens after that. The proton just jumps back and forth between the protonated oxygen and the deprotonated oxygen, and no reaction actually happens. We have to have a reaction happen to change the connectivities. So yeah, the proton can jump back and forth between this O and this O, but when the double bond grabs the hydrogen, or the proton, then we get the ball rolling. And let's take a look at what we have. Markovnikov would dictate that your carbocation will be there, the secondary, but also it's stabilized by this oxygen. And we're going to show that in just a bit, because it is part of the mechanism. So what happened here, the hydrogen, as you know, the rich get richer, and the hydrogen goes on the carbon at the end. The carbocation goes on the carbon that got naked. From this, and yes, we do create water. Okay. So from this species, we go ahead and bring down this lone pair. That's a resonance, actually, right? No atoms moved, but we did move electrons to form a new Lewis structure. Okay. You see, we're getting close to the keto form. Last thing is, we did create water in the previous step. Let's bring it over here over the arrow. And let's go ahead and get rid of this hydrogen. And there's your keto form. And your keto form is a ketone. Now, if you got to think about this a little bit carefully. Well, I don't have that example. What if we had this example here? And then we'll go to the reactions. How about that one? Okay, I'm trying to put these both on the same view. Right there. What is the keto form of this? The keto form of this looks like that. So it seems like if you're up on your classes of molecules, we could get also the aldehyde. But again, this is called the keto form. Okay, it's just the carbon-oxygen double bond. But the actual molecule is an aldehyde because you know that this is an aldehyde, and this is technically a ketone. But you could get either one depending on what your enol looks like. Alright? Okay. Reactions. First one is going to be reaction 9. It looks like, what was it? 9. A, B, C, D, E. 9E. Acid catalyzed hydration. Okay. It's very similar to acid catalyzed hydration of an alkene. The conditions are almost identical. Let me show you that. We need an alkyne. And I am making it terminal, and it's not symmetrical. Okay, we do have, we can't apply Markovnikov's rule here. The reagents are similar, like I said, water. Do you remember what else was in hydration of an alkene? H2SO4. But I'm going to add one more reagent, HgSO4. Mercury 2 sulfate. So we use the mercury plus 2 ion, mercury 2 sulfate. That one is necessary, okay? It can happen without it, but it's going to be kind of slow, and also the regiochemistry is not going to be very precise, okay? Because, you know, with Markovnikov's, do you know which carbon is the richer carbon? This one has 1 hydrogen, and this carbon has 0. Markovnikov, you can think of it as the rich get richer. So your hydrogens are going right here. If you think about what's happening in a hydration, and I'm going to put this in brackets because I want you to know for sure that this is an intermediate. This is not the final product. But if you do the hydration like you know how to do, you would use one of the pi bonds to add a hydrogen, and the other carbon, which is naked, gets the OH. If that's not familiar, you do have to review acid catalyzed hydration of alkenes. With an alkene, right, normally you'd go from a double bond to a single bond and make the alcohol, right? Here we went from a triple bond down to a double bond, but we still have the alcohol. What do you notice about this? This is an enol, and it's the intermediate. It's not the final product. Your 2 dots are still there. We still followed Markovnikov's rule. The hydrogen went on this N carbon, so we went from 1 hydrogen now to 2, and the OH goes on the other carbon. But because of what we discussed, the keto-enol, or the enol-keto tautomerization, we know that this is not your final product. What is your final product? Your final product is this. The ketone. So it's kind of strange, because you know hydration as adding water, an H and an OH. We did that. We added the H and the OH, but because of the tautomerization, we actually don't see it. What we see is an O, and look how many hydrogens we added here now. We went from 1 hydrogen to 3. So we did literally add 2 hydrogens. That's H2O. 2 hydrogens and 1 oxygen. Okay. When you're asked to draw the product, you draw this. This is the product. Okay. You can figure out the mechanism now, okay? Because all you're doing is hydrating with acidic water this alkyne to get the enol, and then we saw on the previous page how to use acid to convert the enol to the ketone. Alright, so you do know the mechanism. I'm not going to go over it. I'm looking at my time. I'm not going to go over it here. Okay. If I have time I will, but most likely not, because I want to get through the other type. But before we move on, what are the points here? You're still adding water, but in a different kind of form, right? We added water technically here, we removed one of the hydrogens. But still, in total, we added an H on this carbon and an OH. So that's water. And those H's and that oxygen are still here. So we still add water or Markovnikov. That's what I wanted to make a note of. Okay. In this case, we form the ketone. Now, if I had used this alkyne with 2 different R groups, 1 on each side. So here on the left we have an ethyl, and here on the right we have a methyl. So there is no rich gets richer, right? Both carbons are equally substituted. When you have that case, then you're going to put the oxygen on both carbons in separate molecules. So we get a mixture, right? We added stuff to both carbons, we add both stuff to both carbons. Hopefully you could do this without going through the enol, because if the professor is just asking for the product, you should know that the triple bond goes away. Right? The triple bond went away. And where are my 2 dots? We have a dot there and a dot there. The carbonyl group could have gone on this carbon, or it could have gone on this carbon. Because Markovnikov doesn't apply here. We don't have a richer carbon. Both carbons have 0 hydrogens. Okay, so the selectivity, there is no selectivity in terms of regiochemistry. We make both constitutional isomers. Now, I can ask you, what enol did this come from? Okay, so that could be a side or a part B of the problem. Well, the enol that made that ketone was this. Well, the oxygen was on this carbon right there. So the enol would look like that, right? The triple bond turned into a double bond, added an H on this dot on the right, and added an OH on the left, and then it tautomerizes, okay, to the more stable keto form. So same thing here. In this case, your enol looks like that. Alright, it's going to take some practice. Admittedly, I did this pretty fast. I really should use the equilibrium arrow, okay, but it much favors the keto form. Let me just change this into an equilibrium arrow as well. Bigger arrow goes towards the keto group. Okay. For 9F, I'm going to use the same alkyne and show you the difference. It looks like for 9E, we put the double bond oxygen on the internal carbon. Markovnikov, because the rich get richer. This carbon that had more hydrogens than the other carbon gets even more hydrogens. It actually got 2 hydrogens, right? Let's take a look at the opposite effect, and that's reaction 9F, Hydroboration Oxidation. Do you remember those reagents? That was BH3. Let's take the same, you know what? Let's remind ourselves about the alkene version. 1, 2, 3, 4, 1, 2, 3, 4. Okay. I'm just counting my carbons to make sure. Okay, for the alkene, this is review. Do you remember the reagents? pH3, H2O2. I'll use NaOH, but I could have easily written OH minus. And non-Markovnikov. Okay, you add something to both carbons, and now my OH goes on the less substituted carbon. Did this carbon here get the hydrogen? Yes, because it started out with 1 and now it has 2. This is non-Markovnikov, the opposite of what you learned initially. Okay. So take a look at the alkyne. This is new. For the alkyne version, okay, go ahead and put your 2 dots. Each dot will get something. Okay. It is the same starting material that we looked at for acid catalyzed hydration. Same starting material, and look where the double bond oxygen went. On the carbon on the left. Here we're going to put the double bond oxygen on the right. The reagents are a little bit weirder. So one reagent is the SIA, SIA, 2 of them, and those 2 replace 2 of the hydrogens. I'll explain SIA in just a bit. The oxidation part is identical. This SIA looks like this. BH. It's a bulky group. And chemists developed this bulky group to make sure that the molecule follows non-Markovnikov. It just accentuates the selectivity. Okay. If you're curious about the name, where this came from, this is I don't remember the name. Isoamyl borane equals SIA. And the di means we have 2 of them. Okay. So sec-isoamyl is one of these groups. Okay. Don't worry too much about that. Worry about your product. And we're going to practice by drawing the enol intermediate. If your instinct for Markovnikov says to put the H here and the OH here, you're going to do the opposite. You're going to go from a triple bond down to a double bond, and now put your 2 dots. Initially, or Markovnikov's fashion, you put the OH here, but now in non-Markovnikov, you put the OH on the end. Okay. So my task to you is convert this enol to the keto form. How would that look like? Okay. How would that look like? Remember the trick? The trick is to shift a double bond. And your final product would be this. Oh, what is that? That is an aldehyde. And this is the product. Oops, a little fast. It is still the keto form. It's still the keto form. Keto meaning that you converted the OH into the carbon-oxygen double bond. Sure, I wish they had called it the carbonyl form, right? Because carbonyl will reply both to an aldehyde and a ketone. But they didn't. They called it the keto form. So this is the keto form. It just happens to be an aldehyde. And we had a keto form that was a ketone for the acid catalyzed hydration. Take a look at those two products, if I could get them on the same screen. Sorry about that. Oh man, I don't think I can. Okay, so let's do this. In our first reaction that we saw today, put your dots, put your arrows. If you don't want to draw the enol, okay, in a scratch sheet of paper, just know that you're following Markovnikov's rule to add 2 hydrogens and an oxygen. The 2 hydrogens go on the richer carbon, and the oxygen has to be a double bonded oxygen. Okay, right there. Now we went through the mechanism to go from the enol to the keto. Alright? But again, if you want to try to jump to the final product without having to draw the enol intermediate, try to come up with some tricks or mnemonics, or how do you want to think about this to get to the product fast. We could put the double bond, I'm not going to do this. You could put the double bond oxygen on this carbon and put the 2 hydrogens on this carbon. Okay, I'll do it. So you could say that, oh, I put the oxygen here and I put the H and the H here. Okay. Again, it's not magic that it jumps to this automatically. We know that it has to go through the enol. Why shouldn't this bother you? This shouldn't bother you because we're doing what we did before. We added an H and an OH to get our intermediate. An H and an OH. You saw that, with alkenes. So here's hydroboration oxidation. Now, look at this situation. Let's put the oxygen now here. And was it 2 hydrogens? Yeah, it was 2 hydrogens. It has to be. It has to be water. So this carbon had no hydrogens. Now it has 2. Again, you could use this as a shortcut to the product, or I think it just takes 5-10 seconds, and it actually reinforces the idea that no, why don't I put an H here, an H here, and an OH here. That's how I would do a hydration in a non-Markovnikov fashion. Didn't I do this here? I put the H here, and I put the OH there for the alkene. Well, technically I'm doing the same thing for the alkyne, but I go from a triple bond to a double bond. Okay, so you could get that squared away. And then you could apply what we learned in this video. The enol will convert into the keto form by shifting this double bond over, okay, and getting rid of the hydrogen. And it will work out. This carbon here has 1 hydrogen. Now it has 2. And yes, we still literally added 2 H's and an oxygen. Okay, they're just in different forms than what we did in the alkene. Okay. It's a little bit tricky, alright? What you want to realize is that let me see if I could do this. No, I can't. I'm trying to get everything on the same screen. Oh no. You see how note cards would be easier? But again, I'm introducing the concepts. It is the student's responsibility to put them into note cards or study sheets in some way that they can be easily studied. So here is on one giant note card the 2 hydration reactions. Okay, let me zoom out so my picture's not right there. And if you really want to clean it up, get rid of the alkene version. Okay, and then you have these two right next to each other. Look at the difference in the products. Okay. All right. I think there's one more set of reactions after this. They're all types of reductions. Okay. And then that will finish up the list of alkyne reactions.